Good morning, everyone. It's our pleasure to welcome you to today's product orientation program. We are honored to host scientists, professors, and other industrial leaders from esteemed organizations such as ASL, DRDO, DRDL, RCI, ARCI, NCAM, NIT Warangal, IIT Hyderabad, Usmania University, BITS Filani, Space Route Aerospace, Skyroute Aerospace, and others. We appreciate your presence here today, and we are grateful for the opportunity to showcase our latest technology products, electron beam welding machine, electron beam melting machine, FDM, and 3D printing machine, additive manufacturing, and our capabilities in designing custom build machines tailored to meet specific customer requirements. Without further ado, we invite Dr. Professor Rolf Edinger to share his insights and present our product lineup. Please take your seat and enjoy the presentation. Sit.
Let's see if this works. Okay. So my name is Rolf Edinger. I'm with Camora Tech. Some people know me already. And I would like to show you a 3-minute movie before we start that has everything we actually do. It's just a short movie. The movie is heavily on defense-related topics. The reason for that is since April we have a political environment that is forcing Canada to be more independent than it was before. And so we have a lot of new projects where we are focused on independent, having our own Canadian sources in material supplies, special machining processes, and so on. So this gives you just a short overview. Let's see if it works.
Aerospace. Power. Infrastructure. The world's most demanding industries rely on.
Do you have a tone?
Performance at scale, built with materials and machines that never compromise. That's where Camora Tech additive manufacturing comes in. Our LEAM-Q platform is a meter-class laser powder bed fusion system, purpose-built for industrial-scale production of high-strength metal parts, from 1 by 1 meters to 2 by 2 meters and beyond. The patented 4Z tank system inverts conventional architecture, fixing the build plate to eliminate deflection and improve geometric stability, while reducing machine size by up to 40%. Each laser operates in its own isolated gas reaction chamber, ensuring stable melt pools, consistent focus, and perfect beam alignment across the entire platform. LEAM-E is our advanced electron beam additive manufacturing solution, featuring the patented 4Z tank architecture and a high-temperature build plate heater, ensuring exceptional thermal stability, geometric precision, and part quality. LEAM-E operates under high vacuum conditions, drastically reducing oxidation and enabling deep beam penetration with accelerated build speeds. The system integrates beam vision and real-time beam control for enhanced process stability and precision. Designed for flexibility, it can be reconfigured for advanced electron beam welding applications. At Camora Tech, we're not just building for today, we're engineering the future of additive manufacturing. This slide gives you a glimpse into what's next in our innovation pipeline, as we extend the LEAM platform into new capabilities like in-process CNC milling and multi-dimensional deposition technology, or MDDT. With in-process CNC milling, we bring subtractive precision into the additive workflow. Typically performed every 5 to 20 layers, depending on geometry, this allows for internal and external features to be machined mid-build, using standard operations like contouring and facing, without removing the part from the build chamber. The result: tighter tolerances, cleaner surfaces, and reduced post-processing. Then there's MDDT, a fundamental leap forward. By integrating XYZ-controlled material deposition, MDDT enables true multi-material printing within a single part. Imagine building a structure that seamlessly transitions between alloys, or embedding functional zones directly into the geometry. These technologies unlock a new class of high-performance parts, parts that can't be made any other way. This is where additive manufacturing is headed, and we're already on the path. From aerospace to advanced energy, Canmera Tech gives you the tools to build what others can't. Proudly Canadian, we combine deep R&D expertise with precision-engineered platforms, enabling innovation at scale. Engineered and built in Canada. For more information, please contact us.
Good. So in addition to that, I would like to say that VS Technologies is our partner in India, and we are actually manufacturing components in India for this machine. And assembly, sometimes we do that in India, or in other cases where we do not Indian customers, we do the assembly in Canada actually. So just to give you an idea that this is a collaborative approach in manufacturing. So what I would like to do is switch to the presentation now. Okay, let's see. What I would like to do today is explain to you why we say we do large additive manufacturing. So when we define large additive manufacturing, we talk about powder bed fusion systems. So not DED, like we are focused on powder bed fusion, but our goal is and was from the start to scale it. So we were looking at scaling the technology into components that are larger than it was envisioned right now. For example, in one aerospace application, we have a request for a manufacturer. They make drones, and a drone component could be 1 by 4 meter. So they have want a powder bed that's 4 meter long, 1 meter wide, and that's actually a drone project. And it's just, at the moment, crazy. People come up with all kinds of ideas, and how do we satisfy those mostly customized systems? Because you can go, if you have a 400 to 600 millimeter machine, you can maybe have standards, right? But if you go into large components, there's a lot of customization required for those large systems. So that was our goal. How do we scale additive manufacturing? Additive manufacturing, in our case, powder bed fusion. And when we talk about powder bed fusion, we have two technologies we are using. One is electron beam, because traditionally I came from EBW, so we said, okay, we still do EB, and laser beam. And when people ask us, okay, why are you having those two, and what's the one versus the other, then I'm saying, okay, if you have high temperature materials, like, and now I'm talking about like tungsten or niobium alloys or things like that, you probably could use EB at some extent, right? But everything else, I think you can do with laser. So I would say 95% of your material alloys you can actually do with laser. So this presentation is now focusing on lasers and what we do with the laser and how we build those laser machines. The first thing is that we are saying when we talk about large, okay, I just spent a week and a half in Germany on Formnext, which is an additive manufacturing show. And I met a lot of our Chinese colleagues there. And for them, large, for example, is already different from large in Europe. Large in Europe is 600 millimeter by 600 millimeter. Large in China right now is 2 by 2 meter by 1.5 meter. So you can see already large additive manufacturing is already in different regions has different meanings, right? Now what are they doing with a 2 by 2 meter machine? So there's different, I saw parts that are that size, so one single part, 1.2, 1.5 meter long, and I saw, I think it was 1,200 small parts in one big build. So they have stacked over each other, across each other, 1,200 different. So additive manufacturing is not just a straightforward technology where you say, oh, I do this and then you use this. So in additive, you can do a lot of things. So it's very complex sometimes to really have a target, but it depends also on your products. What are you actually manufacturing? So that's why you see we have projects from marine application, like for shipbuilding, which is, why would they do this, right? But they sometimes need pump wheels, they need pump structures that are very complex. So you can have that. Aerospace, anyway, everybody knows aerospace is heavy in that. We are not doing much in medical applications, because typically they have small machines, we are focused on large machines, so medical is not really something we look a lot at that, even that we have some technologies. Mind you, we have also a small machine, which is the same technology, and the small machine is like starting at 150 cubic millimeter, so small machine, but that's really for material research, right? Sometimes it's very, materials powders are expensive, so it's very, if you have a 1 cubic meter print, that's an expensive experiment, right? So then we're saying, okay, maybe you do some fundamental material research on a small machine, you have the same parameters, same laser, same settings, and you can do that. So there's actually quite some requests for small machines, parallel with a large machine. So you can do parameter development on a small one and then transfer it to a large machine. But our focus is on large parts. That's really where we think we are the strongest in that sector. Okay, so here's an example. These are bike frames, so literally bicycle frames because they are neutral. And even on the show in Germany, many of the companies showed bike frames, even that you do different stuff, and that's just an easy way to show the sizes, right? So when you look to the left, 400 millimeter, 450 millimeter is your standard, your left, yeah. 400 millimeter is your standard build size. So one of the machines we showed in Germany is 1.1 meter by, so the 1010 is a 1 by 1 meter, could be 1 by 1.2 meter, then we go 1.5 meter, and then we go up to, here's 2 by 2 meter, we go up by to 2.5 by 2.5 meter. So that gives you an idea. That's the build plate, okay? Build plate is X, Y coordinates. Now we have to talk about set. How do we do now the vertical component of that? Okay, so we have three, I would say, three key technologies, about 8 patents over this technology. 3 technologies that actually enable us to do what we do. So the first one is what we call 4C tank. But basically what it is, that the build plate, so the plate that is actually holding your component does not move. It is fixed onto the machine. It does not move. And the tank around this build plate is moving up. And this has the advantage that I can have the stability of the machine frame supporting the structure of our build plate and the component printed on that. So it's quite a different approach doing this. On that build plate, we then have what we call smart powder flow. We have a vibration-driven system that is depositing the powder directly over the powder bed. Because if you have a 2 by 2 meter powder bed, you cannot just take a rake and then rake powder over it. So you need really exact dosing in X, Y, and height of your powder layer that you get that actually deposited in the way you want it. It's very, very important that you have a flat and dense layer that you start printing on. The third one is the laser system in this case. That could be an E-beam, but in this case it's a laser. So when you look at the laser system, we did research and we did studies, and I show simulations in a sec, that typically you have galvos. And I'm not sure if everybody knows that, but galvos are basically 2 mirror systems where the laser beam is actually bent and scans over the surface area and melts the components. This is the standard AM approach, right? We have more something that is more you would see in laser cutting and industrial. So we are not bending the beam, we are moving the beam over perpendicular over the surface. So the angle of the beam never changes. It's always constant vertically down onto the surface. And then people ask us, why are you doing this? Nobody does that, right? It's not quite true. There's another company doing it, but they're doing it a little bit differently. Okay.
Can you just, studying an analyst, can you just repeat how the beam is made vertical all the time?
It's moving in X and Y. You will see that. So the beam is moving in X and Y over the component. Each beam has its own X, Y coordinate system, similar like a galvo, that can actually move over the surface. So the reason why we do that is these 3 simulations are now showing the galvo approach, right? So the left is a CFD model of the beam when it starts. So let's say we start in one position, then we move over the area with the other position. You can see that the heat profile in the heat affected zone is totally different, and the sweet spot, how this thing is actually melting the powder, is different from the vertical or the end position. You can see when you actually make bended melt pools in one direction, vertical, and you cut them and you look at them in the cross section, they look completely different, okay? So now imagine you're printing a large component and you're using galvos and you try to hope that you get the same conditions. It's impossible, okay? You can correct the focal point, but you cannot correct the melt pool because the beam is still at an angle. So we said, okay, our goal is we wanna be vertically. The second problem we found is when you angle the beam, there is a lot more porosity. So you will see that there are these little bubbles in this, let me see, here. You see these bubbles here. These are actually defects, okay? These are literally little gas bubbles that created in the melt pool. And then you can see that, especially in the beginning, is a lot there. Here are some. That's how the flow of the metal is going into the melt pool. And in the vertical condition, you still have them, but less so. At least you can find the sweet spot, right? So we said, okay, we want to optimize our process and find the sweet spot of the melt pool, and we want to, it could be either one of those, right? So you can have either the left or the right, but you have to fix one angle. You cannot just constantly change the angle with the galvos. Now, the second point is, on a small machine, that's okay, but now think about, you have a 2-meter machine, and then you have this, right? So you get this times so much more, and you have a lot of porosity in your components, and people report that. If you look at the white papers, people are reporting that. So we said, okay, we want to stick with that. We want this to happen, and this is happening inside the melt pool, right? So in our case, we said, okay, we want to have similar like industrial machines like laser cutting, laser welding machines. We want to have the beam vertical, and we move the beam very fast over these surfaces, and that's how we generate the same trajectories like a galvo would do. So that gives you the reasoning why we are not using galvos and why we are doing this. Now I want to go to the second story. So this is inside the melt pool, but as you can see, this is a plasma, okay? Most of these melt pools have in the core, in the center, they have actually a plasma, which means if you create a plasma, that comes out, right? It could be metal vapor getting deposited on surfaces, whatever, but if you have high concentrated energy, the plasma goes backwards out of this. So now what's happening when you get this out of this melt pool, right? It seems to be small amounts, but it's constantly, and it's actually building up over the surface. Okay, so let's look about the above the sequence.
What is the height between the molten pool and because always you are maintaining a vertical beam, right? So the plasma may get deposited on the optics also. Is there any
Just
provision?
wait, I will get to that. That's the answer here. So now you get this reversed. So on the again, the left side is your standard galvo-driven system, okay? Let me just get the mouse here. As this gas, this is the inert gas protecting the powder, moves across the surface, this plasma shoots up, okay? And then in the following end of not this side, the gas hits the melt pool, behind that, there's a low pressure region, you can model that actually. And that low pressure region causes a lot of problems. So we said, okay, and it makes a chaotic gas flow in here. And you can see that if you look at the standard machines that use galvos and go in large angles, you can see a lot of these black suits sometimes coming out, right? And depositing dark particles over the surface.
Actually, I have seen in the previous slide, the vertical
it's moving. The beam is moving, right? So so which one? The vertical?
Vertical.
The vertical beam is asymmetric because it's the cool down. If you move the beam from left to right, then you have a hot zone, so it solidifies here, but it heats up the front. So this is a moving beam. So the simulations are actually like what happens. They are moving over the surface as you would move in the melt pool.
Okay.
So that's the cool down phase actually.
Okay, good.
So now we go to the question, okay, yeah, but if that plasma comes out, what's happening to the surface, right? So each laser gets its own reactor chamber. Okay, so around the beam that goes on the surface, it starts the melt pool. So the thing that happens when you look here is the gas comes out. So we create this zone 1. So zone 1 is actually the melt pool recoil pressure. It's coming out of the surface, right? So there's a gas jet. Let me just grab here. The gas jet coming here, that's stopping that. So step 1 is you stop the gas going to the optics. That's step 1. Then on the outside of that, let me just stand up, I think I prefer that. So on the outside of that, you actually have here a second gas stream that's reacting the gas. So you have two problems. One is the reaction of the hot gas. You have to stop it, that it doesn't go into your optics. The next one is, now you have to cool it down and react the components that are in the gas from the recoil pressure, you have to react that. So it doesn't solidify somewhere, right? So that's in that gas. So that's the second part. So that's the second is the gas insertion zone. So that's the zone around it. And then the third one is the reaction zone. So this thing is up to 250 millimeters long. And the thing is, why we have this length is that we have enough time to react what's coming out of the powder with the inert gas before it actually goes out. And then the fourth zone is that it goes out, there's a gap in there and it goes out. So there's still gas on the outside, but every beam has its own protected area and the gas is coaxial. So it doesn't flow across, it's going coaxial with the beam down onto the surface. And it's to protect the optics, to stop the recoil pressure, to react this, and then to cool it down and to get it out. So it's quite a complex process. That is why we don't use galvos. It's just a process. Does it answer the question? We discuss later. Okay, good. So the first level was to have this laser beam always operating in the sweet spot. You do not get porosity. You can melt the exact parameters. You have constant velocities. The line energy is constant. The angle is constant. Also the volumetric melt pool, the volume that is described around the melt pool is constant. It's not a changing number. So that's why we have it this way. Just to keep the conditions during the process equal. So then we talk about powder feeding. So powder feeding for us means we can feed powders that a lot of people cannot use. We have a lot of good results with, for example, totally random formed water atomized powders. So these are very low cost, right? But they cannot be used because they don't flow. They have zero flowability, right? But because we use actually a vibration-based system, we can basically make them flow over the area and we just make them into a layer. Okay, that's part of this. The other thing we found is, because we use this vibration system, is that when we have these powders, we create higher densities in the powder bed. Because if you have spherical powders that are very good in flowability, they create a lot of empty space in there. If you have asymmetric powders, they can actually create some, when they form them, they can create better densities in the powder bed. So but that depends on your powder and the material you want and how the powder was manufactured, right? So that's own science in itself. Powder manufacturing is actually a big scientific group. But there are actually a lot of low-cost powders. If you think the powder, when I talk about water-atomized powders, all your car gears are made by powder, PM, because they just injection mold them and they sinter them. So how can it be that powder is expensive? If all your cars that are, you say they're expensive, but they're actually cheap, right? So cars are cheaply made. So many, there's like 15,000 parts in a car. That's a lot of parts, so each part has to be cheap. So how can they use powder metallurgy for automotive, and then in AM everything is expensive? Because in AM we use the wrong powder. There are low-cost powders available, right? There are steel powders. They are not titaniums. They are not this. But they are for fixturing or for other things. They are powders made by other processes that are low cost. So then why have we those expensive powders? It's because they have no spreadability. You cannot build a powder bed over that. So you need different technologies in order to utilize those lower-end powders. And they're lower-end because how they are manufactured. So that's part of the feeding process of the whole thing. But I think even that is okay. So here this is a picture of just recently in Germany on a show where we displayed a 1 by 1.2 meter build plate. The thing is, how do we create these stabilities, right? How do we make a flat components? How is the part actually, when you print it, coming out the way you want it? There's a lot of things that are thermal through the hot and cold cycles, deformation, stress, and so on. But a lot of this can also be in the machine, right? How stable is the machine? How do you process it? So our goal was, okay, we don't want to move the part. And the reason for that was downstream, we also want to do machining. So now you saw in the movie, we talk about CNC machining in process. I don't talk about that. Either customers like it or they hate it, to be honest, right? We are doing it because we want to make complete parts coming from the machine. So at some point in the future, we want parts coming out of this machine. That's part number one. Part number two is, I'm talking to an aerospace company in Montreal. They are printing a lot of parts right now. So I give you their question, you can answer. So okay, they're printing fuel nozzles right now. How do you make sure that the fuel nozzle, so it's a complex shape inside this component, has the correct roughness, surface roughness, and dimensional accuracy? How do you do that? Even if you use a 15 micrometer powder or 20 micro, which is very expensive and complicated to process, but even that gives you not the surface roughness you want. So then you talk about nano powders, that's crazy, right? So that's even more expensive, right? So how do you create a component that has an internal flow that has the surface roughness and the tolerances you require for your component, but it cannot be accessed after printing from the outside through machining? So how do you do that? Okay, so they have no solution. They are challenged with that, right? And based on their requirement, we started with machining in process, right? So we're saying, okay, we want to have a little bit of machining every once in a while. So let's say we build, when we talk about machining, we are building a couple of layers, 10 to 20 layers, we start machining. But that requires that you have a stable platform. Now I'm not talking about really a printing machine anymore. Now I'm thinking, okay, I need to be at least stable to have micro machining capability. So when we talk about machining, we are not talking about taking off 10 millimeter or 100 millimeter of material. So we are oversized printing 50 to 100 microns, and we are only machining this off, right? We are running a program right now just for the machining of these material in Montreal. It's also with Airbus, and we are using liquid nitrogen for that. So there's a lot of technologies out there that are actually now pushed into the aerospace sector for many reasons, and the reasons how. So why do I bring this up? okay, in order for me to machine something very accurately, I need a platform that's stable. If you have a build plate that can flip around and I put a machine tool on there, it will deflect. So I cannot machine, right? So we said, okay, our build plate has to be mounted onto the machine like a machining center and does not move. Okay, but we need a tank because we talk about powder bed fusion, right? So then we came up with this, which is patented, with this tank that forms itself. As you go up, the tank forms itself as it goes up and forms a tank around it. So the most important part is actually not the tank. When you look at other machines, they put a lot of money into the tank and this stuff, right? But that's not the most important part. The most important part is the build plate and your part, because that's actually why you buy a machine. You buy a machine not because you want the machine. You buy a machine or you run and operate a machine because you have to make parts, right? Whatever they might be, however they look like. So we said, okay, let's focus on the part. Tank is secondary. So now that the build plate is fixed and allows us to the machine. So it's not only one reason why we choose this, it's like the complexity of things, right? So CNC machining, again, I tell you, either people like it or not in process. What's the disadvantage why they don't like it is, okay, now you have metal chips, right? So I'm doing this, I'm having small metal chips in my powder, how do I deal with this, right? But by designing the machining process, I can make metal chips that have the same size as the powder. Okay, you can, if you want, you can deal with these issues. The question is, do you want it? So these guys, the Montreal guys, they have their problem. They have not found a post-processing where either they get the surface roughness, then their fuel nozzle diameters are out of tolerance, or the other way, they get the tolerance correct, but then the surface roughness is never what they want. So it's always a challenge to do that. So we said, okay, there has to be a technology where we do an intermediate step. That's why we developed this type of machine that looks very different from anything else you might see on the market there. Right now, I know only of one 2x2 meter machine that's made in China. The 2x2 meter machine needs 64 lasers with galvos. Okay, now that may not sink in. 64 lasers with galvos, this machine is very, 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 very expensive. As a matter of fact, it is so expensive, we had Chinese customers on our booth asking for machines because they said, we cannot afford this machine. They would like to print 2x2 meter parts, but they cannot afford the machine. 64 lasers is a lot of money, it's a lot of power, and a lot of waste. It's cool, like as a machine builder, I think it's a cool project to build this machine, but is it really for the customer usable? Very difficult, okay? So we said, okay, when we have a product, or when we know our customer, how much volume is your part? What are you actually printing, right? So for example, you may need a 2 meter print or 1.5 meter. Let's say 1.5 meter. You need a 1.5 meter build plate. But maybe your part is a ring that is 1.4 meter in diameter, but only weights, let's say 30 kilo. It's very lightweight, right? So then what are you doing with 64 lasers? Most of them cannot access actually the ring, right? So is that really the best use of your money in order to produce those parts, right? So we said, okay, we look again at customization. So we can have, we can vary the number of lasers. Some machines, the minimum you require is 4 lasers, okay? Starting from 1 by 1 meter, you need at least 4 lasers. So what's the maximum number? So right now, it's a control issue and it's a cost issue. We are limited to 24 lasers right now. So we can go from 2 to 4 up to 24 lasers for this. But it heavily depends. If you have a lightweight structure, you don't need 24 lasers. Maybe you're okay with 16, right? Really, it depends on the weight and the volumetric you need in order to do that. So again, that's why we are not using galvos, because each laser needs to be accessible in each of these areas, right? Yep. you need more size. Then you need a 2-meter machine. If you have 1.5, I would not, you can. You need 2 by 2 by 2. You still need more than one. If your part is exactly 1.5, you need a little bit more size. I would not print right to the edge of the tank. There's too much variation, right? So you need, maybe not, you don't need 500 millimeter, but we say typically you want something between 50 to 75 millimeter around your component. That's the powder bed, and that is just to have a stable environment in there. So if your part is exactly 1.5 meter, 1.5 is too small actually. You need just a little bit bigger than that. Yeah, or 2 in this case, 2. But we could probably do 1.7 or something like that. What is maximum size? Right now so in square 2.5 by 2.5 is the cross section. Height doesn't matter. Because we don't care. The build plate stays on the thing, on the floor. It's basically not on the floor, but on the machine base. The machine base is on the floor, the plate is on there, and you build the tank up, so it's just shafts. You just need more guideways. No problem. Yeah. But again, if you think about conventional machines, right, they would need, if you go 2 meter, I have a picture I can show you later. It's a 1.1 meter set, so the whole machine is 6 meter high. Because you got the laser, first you got the lasers, then you got the tank, then you need 1.1 meter, then you have a shaft, and then you have a drive system that builds all vertical up. That's the shafts, that's the machine structure, has guideways. Yeah, but we measure the formation, it's just the machine structure. It's like a set stage. Yeah. Thermal management is anyway, we do that internal in the machine. No. Because there's 4 bore screws. Everything has ×4. So each corner has a bore screw. Each corner has its own drive system with absolute encoders and has a measurement system. So we measure exactly where this thing is. That depends on the powder. That depends on the shape, on the particle size. You cannot answer that question. I cannot answer you that question right now. Yeah. I have photos too, but it depends what you're using. So what I wanted to say is, okay, you can customize the machine based on the volume you actually want to make, right? Because if you use a lot of lasers, you need a lot of laser power, right? Think about 64 times 1 kilowatt. That's just for the laser. You're looking at times 2.5. So you had 150 kilowatt of electricity just for the lasers. That does not include anything else around that. So there's a lot of costs going into this process, right? So what do you actually need, right? So that's why we came up with what we are doing, because we try to be very recognizing cost is a key element in this thing. What you see here are our new HMI and CT cam. So the top picture shows you the actual machine interface. That's how you run it. So that's what the operator will see. He gets information of all the information. We're working with Beckhoff Automation now, which is a German company that does controls. But we have a special version of that for our machine. And each laser is its own coordinate system, can be controlled independently. And then below is the CTM slicer. This basically you import your part component, and that's how you generate the code for each layer. how the beam is actually moving over this. So this is also Python based, and we do a lot of customization with customers right now, because some customers have very specific applications. I can tell you that from our market right now, we do mostly stuff the others can't, and that's a lot of work for us. Because if we only do the stuff you cannot do with a standard machine, there's still a lot of materials and parts left to be 3D printed. And it could be size, it could be material properties, it could be a lot of these specialized requirements. And then what we do, that's maybe to that question, what we do is we compare our processes in two ways. So we compare it with components that are made by our competitors. That's the gray ones. The orange ones are what we do. The blue stuff is typically we buy bulk material. Like for example, in this case, we bought titanium 6.4 from a supplier certified material that you would buy for CNC machining. We cut it into samples, and then we compare it against printing, right? So that's one way how you can benchmark your process, is by you buy the material you want to use, like a titanium or an Inconel or whatever it is, you buy that raw material as a plate or something, you cut tensile bars out of it or whatever you want to use, and then you compare that to your printed components, so you get benchmarks about tensile strength and so on. So there are processes. Typically, in a print, you have all it's not only the part you print, typically you print a lot of tensile bars and test samples with your components you can then take off and use for verification of your print. So this is just a technique. Okay, so specification actually 2.5 by 2.5. 2.2 meter is the net shape. Then if you have a 2 meter component, you need a little bit bigger. That's why 2.5. Lasers, one really for small machines. If you have the small 150 cubic system, that's a one laser machine. That's for process development. But then for the larger machines, actually typically we start at 4 lasers. You have 4 lasers and up to 24 lasers. That number will go up in a couple of years. There's a control issue right now. They are working on increasing the number of systems we can have in the control system. And they are talking about 250 lasers, right? But that's still a lot of lasers and money you have to spend. Layer thicknesses, depending on what you want to do, what powder you're using. Layer thickness is not only by machine. So if I have a very coarse powder, I cannot print fine layers. So you also need fine powder. So layer thickness are programmable, similar to other machines, basically. And that's kind of the overview over this system. So here's a little bit, you saw that in the movie already. I'm not sure if that started. No. So here we are talking about machining in process. That was one of the early ones, just to visualize that a little bit. It's in the powder bed. This is now very different. It's becoming its own technology, actually. We are working with the NRC in Montreal on that, which is our research council. Yes. So how this works is we have the laser level, and above the laser level we have another level, which is the machining spindle, and that comes in. We did a lot of this, but then we put a little bit of a break on that, and the problem was, especially with titanium, was cooling. So we had an issue with cooling, right? And then through some connections, I found out that we have actually a big project in Canada that is replacing traditional coolants with new technologies. So there's minimum quantity lubrication, MQL, and then there's liquid nitrogen cooling, right? So in our case, I said, I'm interested in, so we have a program right now which is then joined by others like Airbus. And it's all about GHG, like greenhouse gas reductions. That's their main in aerospace sector, reducing greenhouse gas emissions. So they want to get rid of this. So, but for us, this is an opportunity. If we have liquid nitrogen, we can now cool our tools. So we are running a program right now. It's in the final phases till mid next year, where we inject liquid nitrogen into the machining process to cool the machining tools, and has very good results. Surface finish, the speeds are very high, much higher than non-cooled applications. So that's kind of where we are right now. The other thing is something I must say.
Once you machine it with liquid nitrogen, what is the effect on the next project?
That's what we're working on right now. That's exactly the program we're working on right now. Yeah, we have the components are heated, right? But the liquid nitrogen is going towards the tool, not to the part. Because it's tungsten carbide, it's really directed at the so it's more in heat extraction than really it's not the same machining you would do with a conventional, right? We are just machining, micro machining really, right? Just to get surface finish and tolerances. As a matter of fact, we want to machine as little as possible, right? We need to print a little bit bigger because that's the only way it works, but we want to machine as little as possible. This is still work we are doing, right? Development work. It depends also on the sizes, how big you're printing. Then the other technology we started, because we started from a different direction. The direction how we started was actually alloy development. Okay, how can we develop rapidly new alloys? That was our goal. At the moment, due to funding, we gave up on that, okay? We had a meeting, we have an international project with DLR, which is the German, it's called DLR. It's a large, also aerospace research facility, and we have that with our university. In that meeting, it was clearly stated that no one in aerospace will pay for alloy development. So we are talking about a new Inconel, a new this or that. Nobody will pay for that. Nobody will accept it. Nobody will build a plane with a new alloy. Okay? So there's literally nobody will take the risk building a jet engine with a new material. That was the status where we ended, right? So then we said, okay, then this is pretty much, that was the idea in the beginning, right? But then what came out of this meeting is saying, okay, but that doesn't mean that you can combine alloys, right? So if I have an Inconel that is already approved, right? And I want to have a component, for example, we talked about copper today, or anything else, you want to have another material. In this case, we have a copper and titanium, which is a heat exchanger. We have a customer that wants to do heat exchangers, right? So now we have copper and titanium, which also works actually very well. So now we can have approved alloys that are in itself approved by aerospace or whatever, but we combine them in one component. Because typically you would do that, you would make two components and then you would use a brazing process or some other technology to actually join those components together, right? But they don't like that because now we have a third material. This is the brazing material. So actually I make it more complicated. And by the way, instead of printing, we have this heat exchanger has, I think, 17 components, 17 components right now, and they want to do one print. I mean, that alone saves a lot of money, right? Just by having not 17 parts that you put together and then you braze it, because that's what they're doing right now. So they want to print it. But you need to print titanium and copper, for example. So they want to do this type of process because it will reduce the cost dramatically on the component. But not in the alloy development, but existing alloys combinations, right? That's, I think, our goal. We are going now with that. So that's why I'm saying the alloy development, nobody wanted to do that. Even that you have the technology, everybody said, No, we are not touching that. That's too much for us. But then, which I disagree a little bit with, but doesn't matter. That's a different story. Once it becomes strategic, we talk about alloy development. Right now, we're talking actually again about alloy development. We're talking about this because our friends in the south said no more support. And so now we are stuck. Okay, what are we going to do? We are not having a defense system in Canada. We are not doing this. So now we're talking about alloy development again, right? So it depends a little bit on politics as well. Do you want to be independent or not, right? But the real commercial goal right now is existing materials that can be combined, right? So dissimilar welding, if you have materials that work in dissimilar welding, you can print. Any dissimilar welding materials, you can actually print. You can probably more, but at least that part where you already have technology and you have to say, hey, I've welded this material with that material, right? Or I've done this with that. All these materials you can actually print. So that gives you an advantage. So now you can combine different materials. Okay, so this is a little bit what we do. And some of that will be done with us. VS Technologies is our partner here, and they will set up the mechanical structures and things like that, and then we can do the total integration there.
Shall I see the presentation? Shall I give some presentation or VS Technologies?
You can do that if you want to.
Can you finish it? Have you finished it? Have you finished your presentation?
With laser, yes.
Okay, once completion, then we'll come back.
Okay, you can do that. We can do later, and then we can do some questions right now.
Yeah, good morning to all. I am from VS Technologies. We have already existing units at Challapalli, manufacturing facility we are having. We are collaboration with Canmara Tech, Canada. We are one more unit has started in Nadarkal also. So we are continuing with the business with Mr. Rolf Edinger. And the marketing is MTI peoples. Thank you. We are also giving some miscellaneous specialists and everything we'll show.
Yeah, we do that later. So maybe we can go through some questions right now based on what I showed you here. Just wait.
In case of this two powder mixing and making a part, so will you be able to separate those powders?
Good question. If they are, for example, if they are magnetic and non-magnetic, it's very easy. Okay, so the one way is if you have a magnetic material and a non-magnetic material that reacts on magnetism or not, then you can separate it. Another way we are thinking of right now is particle size distribution. So if you have, you can buy powder in one particle size, like I can make very large particle sizes, and one in a very small particle size. There will still be some, but you can pretty much get that separated. So there's a challenge with that, but I think there are techniques how you can overcome that.
Maybe if different density you can use.
Yeah,
that.
density is one, particle size is one. And then I talked to a company, they make vacuums. They have actually what they call a cyclonic system, and they are working on it to separate particle materials based on the centrifugal forces. So they are working on it already. They don't have it right now, but they are working on that.
My another question is in your large area system, as you said, you are not spreading the powder with a rack or blade.
We have a blade.
Okay. So
we have a blade and a distribution, but the blade is very different.
Okay. So you will be spreading powder for the entire 2 meter in one go, and then you will start printing with your nozzle, or you have a different technology for that?
So the system moves on its own axis and drive. So the system moves from, it starts one side, it puts a layer down, it stays in that position, and you start printing, and then moves back, and then it starts printing. Yes?
Thank you.
You're welcome. Do you have a question?
So one layer, one material, next layer, change like that?
Actually, that's simple. That's no problem. The problem is not multi-layer. Layer is simple. The problem is X and Y.
Yeah, that's what I was also asking next question. How are you now? You shown that titanium to copper
Yeah.
bimetal deposit you made. How are you spreading this powder? Do you have a separate tanks for spreading this titanium and
So these-
dispensing titanium and copper?
So each material gets its own nozzle.
Okay.
And there's a lot of nozzles, so you can then control each nozzle. So you put powder in X and Y here, powder X and Y there.
The feeders are different. For different feeders are there for different materials. Is it so? Nozzles and the feeder also. Tank also should be different, right?
So there are individual nozzles, like there are 100 nozzles.
Okay.
And then there's 2 rows of that. One row would be titanium, one row is, and then you just tell it to a certain XY position, I want titanium here or copper there. So you separate that.
Okay, like a matrix you made. Matrix of
like it's a
nozzles.
matrix. Actually, literally, it's like an inkjet printer. Similar, like where you have different tanks, and then you put the color in a different position. But this is like with metal, but same concept.
What are all the other combinations you tried? Could you find any crack between titanium to copper while depositing?
That was okay. It depends on the copper and the build temperature.
Okay.
So there's a couple of parameters you have to do that.
We require some injected. What is the minimum hole size you can print?
Minimum hole size. Printing only, no machining afterwards, or with machining.
Okay.
Printing only. Millimeters, it depends on the length.
Okay. Okay, I understand, welding we have good quality standards
Yeah.
for printing. So you don't.
There is now a ASTM group forming that is supposed to be coming up with a printing standard. But right now, as of right now, there is not much there.
So what is your recommended practice after the component is manufactured? What you want to do?
So I think we apply, to be honest, we apply welding standards. Honestly, we apply, like for example, it's funny, but we are using EBW ISO standards for AM because we're saying, okay, if there is nothing there, so for example, the in this case, it's the weld speed accuracy or the positioning accuracy. So you can apply those individual standards, and then you can say, how does this, but it doesn't tell you how it reflects on your AM process. That is not, there's nothing there really. So you can only say, okay, I have no standards, so what am I going to do? So I pick some of them, right? The ones I think they are representative the most at this moment, and then I try to apply those.
And one more question. Generally people, they use the powder when you use, almost 40 to 50% it is not melted because due to our requirements. How many times you can recycle the powder?
We have used used powder.
We had some problem, that's why I asked.
Yeah, we have used, and there was it was rejected for medical applications because of the oxide content. We have not found any times, like purposely we're printing with it till we can find there is something we can actually detect. There was no degradation in porosity, in tensile strength, in elasticity. There was no problems in there. So the problem is more in many cases, the particles accumulate. Okay, so we had one, let's say, new powder. It's really nice, spherical, right? But then sometimes when you reuse it, they accumulate. So you have 2, 3 particles stick together. So now you're talking about a different particle size, really, because instead of 100 micron, now you have 300 microns or whatever the number is, right? So that causes you more problems because now your whole spreading process, your whole layer process, all of this. So it depends a little bit of what's actually the issue. Typically, if you reuse the powder, the first step is that you do not have the same particle distribution anymore. You do not have the particle sizes you started with, right? Then you add, so that's the mechanical side. Then you add some oxide on that. So if you're sensitive to the oxides there, but in laser that's less the part than in E-beam. In E-beam you have a lot more oxide build up sometimes than actually in laser systems.
Okay, good. This combined one, titanium and copper, it's very interesting to note. Maybe the strength-wise it might have come down from titanium to slightly lower, or maybe more than copper. Same way, the conductivity may be less than copper and more than titanium. Have you done any experiment for strength as well as conductivity?
So, can you rephrase that a little bit?
Yeah, because for example, generally for heat exchanger, okay, in rocket thrust chamber also more or less heat exchanger. Now we are looking for a material which should have more conductivity, so copper is good, but the strength is less. So here you are combining both titanium and copper. It is a good system I think we can use for rocket chamber. So in that case, what is the conductivity? Are we away from copper or strength-wise? Have you done any sample and tested?
So there's 3 problems actually. So there's the copper, you basically have whatever that is. Whatever the copper you use, you get very similar characteristics, conductivity and other things, right? And then the other side, let's say in this case titanium, you pretty much get what is there, right? The problem I'm not sure about right now, and we are working on that, but it's very complex, is the transition zone. So where you have the transition between the copper and the titanium, you create a new material actually, right? It's between alloy 1 and alloy 2, but you have actually a dissimilar metal there because you're joining that and you get some melt pull in there. That is actually the question, what's happening in there.
Okay.
That I cannot answer you right now.
Okay. Maybe during the design time itself,
yeah,
conventional fabrication and 3D printing, the design has to be, there should not be any support forming inside and other thing. Do you have the tool? Suppose if I give you a component,
yep, we could do that, yes. Okay. So for us, for our business, I didn't say that, for us, we do 2 things, right? So for Canada, we decided not to sell any machines right now. So in Canada, we are not selling machines. In Canada, we're providing service center. So we actually make components for customers. And the reason for that is, by the time, and there are some people that will know exactly what I'm talking about, by the time we have trained our customer that they know what they are supposed to do, that's 5 years later and they still have no parts, okay? So we said, forget about it. That's not going to work. There will be only negative, there will be no progress in there, right? So we said, forget about it. So in this case, they can come to us, we make components, and then they can get the parts.
Okay.
But when we talk about other countries, we're actually exporting the machine, but that also means that we have the capability, we can make components. Okay. That is why I said we also have a small machine, because you don't want to spend and make first a 1 meter component if you don't know what the zones are. So you want to do that on a small component. Okay, now I feel confident I can do that. This looks good. This is what I want, right? Now you just scale up. It's not a fundamental thing. It's like, okay, now I go from the one this size to that size, right?
Okay, one more question is post-processing after the printing.
Yeah.
Do you suggest stress leaving or SIP or HIP so that the densification can be done and to improve the strength?
So it totally depends on what you want to do, right? I can tell you that there was some British company that makes jet engines.
Yeah.
And they spent a lot of money in this, right? So they so they used high temperature isostatic pressing.
Yeah.
So they did
Even
that.
casting, if they are,
For example, so that
Yeah.
you print the part, you make it, you hip it,
Yeah.
right? And after hipping, it looks okay, right?
yeah,
Like, but is it really okay, right? Because my CT scanner also has a limitation. What does it see actually? It looks okay from whatever I use, right? So then what they did is they spend a lot of money. They run the hipped components through heat cycling, what their engine would see, right? And then they found out, oh, this is coming back. So the porosity that was initially in there, after they hipped it, after hip it was gone, but then because even if it's a couple of nanometers, it executed through the heat cycling, some of those came back. So they were not eliminated. They don't show up in your scans, right? But that doesn't mean they are not existing, right? So then they did that was very expensive. They heat cycled the components, and a lot of those defects came back online, right?
okay, last one question. When you print complicated pieces with internal cavities and other things,
Yeah,
some of the unmelted particles to remove,
yeah.
it is little difficult. And some people suggest forcefully some slurry can be pressurized through the channels and the holes to remove the unwanted particles inside. Do you have any technique, or what use you are
So that's exactly what I was talking about in process machining. So the nozzle, the fuel nozzle, right? Some of the particles that are stuck, when I talk about the surface roughness, actually it's that sometimes these particles are stuck so strong only, right, that you can't get them off really. So then that company, what they use basically, it's like chewing gum with an abrasive, right? And they press this through, and then they try to remove it, right? But then if they get sometimes the surface roughness, they're out of tolerance dimensionally. So these processes have a disadvantage. They are not precise enough, so they can maybe give you one or the other, but they don't give you both. If you need both, I think you're left with machining. I don't think initially people said 3D printing, additive manufacturing, oh, we will replace machining, right? That was the big thing. I don't think that's going to happen. I think you have to have a combination of things, right? If you can access the part from the outside, you can easily put it on the machining center, machine the outside, right? No problem, right? But if you need something that has internal structures, how are you going to do that, right? So all these post-processing steps, they are available, but they also cause sometimes issues.
Okay. Thank you. One more is, do you have literatures on shrinkage effect? For example, I require a 1 millimeter hole.
Yep.
If I print,
Yep.
after the all high temperatures when laser is printing and other thing. So systematically depends upon the hole size and other thing. We have to account during the design itself the shrinkage allowance.
Yes.
Do you experience such things in your machines?
So typically we put that into the slicer.
Okay.
So in the slicer, I didn't really mention that, but we developed an FTR model. So what that is actually a very simplified thermal simulation model. It's not very good. It's not like in Abacus or some high-end software. But the thing is, you can run a whole model in an hour, right? It's very fast. So based on that, what we did is, there are some algorithms in there where you can model the temperature as you print. How is this temperature actually in the component? And if that temperature is not equal, you will see a lot of different shrinkage. You will see a lot of different like stress, things like that. That's all about time temperature of your print. How hot, when is it how is it cooled down, things like that. So we developed that. This is part of our process where we run this through what we call fast to run modeling. And it's really, we did that in the university. Basically, it's kind of a simplified FEA for thermocycling this. But the idea is that you can run the whole component, let's say in an hour or something, right? Which you would, in high-end program, may take a week or two, right? So that's why we run on these simplified. That gives us some feedback on thermal management, right? That goes back to what you just asked.
Thank you. Thank you very
You're
much.
welcome. Thank you.
What is the minimum size of cavity you can print on this machine? Cavity, wall cavity inside.
So like just like the whole size. So small size is 1.5 millimeter.
1.5 by 1.5 rectangular type of cavity
Yeah.
you can print?
Yeah. But there's the radius from your powder. So you end up having a radius from the melt pool. You cannot cheat, we try to, but we cannot cheat surface tension and some physics, right? If you have liquid metal, you cannot cheat that. That's the reality. There's metal there, and it does sometimes whatever it does. So it pulls the corner, and it's not a sharp corner, it's actually a little radius in there. Yeah, yeah. There's nothing you can do.
So for in situ machining, every time you have to move up and down this 4G tank, correct?
Yes.
Okay. Then
No, for machining, in situ machining?
yeah.
No.
So
The tank stays in the level,
okay.
the laser moves in the parking position, the powder system, and the spindle moves in and goes in and comes back out.
Then that will limit the depth of the tool, how it can go.
It goes in there, it machines it, and it goes back.
And I have one more question. You were telling that always keeping the laser beam perpendicular to the surface.
Yeah.
Okay, now let's say we are printing the oblique part, which has an angle. Okay, so let's say 30 degree or maybe 35 degree. So now the microsecond, microsecond wise, it will not be always uniform. Like if you are printing vertical wall, that is one part, and if you are printing oblique wall.
You see, from a microstructure perspective, so first of all, everything is in slices, everything is perpendicular. Even if you take a slope, if you print a slope, it's still perpendicular on that layer. It's just at the end, it creates this, whatever the metal is doing, it's creating the slope there, right? So there's nothing you can do. But the laser goes perpendicular. So so you have always to think this is like one layer, and then you have an XY position, and then you have the melt pool there, and you have to run this over there.
Have you made a EB-based powder bed system also, or is it laser-based alone?
So that was the next part, but I wanted first to answer this question. So we basically have the tank technology, and all the powder technology is also working in vacuum. That's part of why we use vibration. We are not using gas fluidization, because that won't work in a vacuum chamber. So that's why we're using vibration systems, and we found out this is actually working very well. We actually delivered the powder system. We already delivered the second system for the powder to the largest military complex in the world. And they can do stuff they could not do that. So it's larger than anybody else, so you can figure out who that is, right? So the largest guys, they're using for certain things these powder feeders. We're not building the machine, we just delivered the powder system because they could not feed the powder accurately enough to where they needed to be. But there's a lot of powder applications for different things, right? So just wait a sec.
Suppose if you are trying to build a single part of 2 meter by 2 meter, how we are managing the distortions?
Which one?
Distortion. If you are managing if you are building a 2 meter by 2 meter part on XY,
yeah.
How we are able to manage? How we are managing the distortions? Bigger part, single part.
How do I manage?
Distortion.
Distortion. Yeah, that's the problem you face because the plate is very thick and it's not moving. You see, that's exactly, that's a wonderful question. The build plate is mounted flat onto the machine, like solidly. It does not move. So we are not seeing that structural change there.
But suppose that distortion while printing, layer by layer, when you are printing, some distortion may occur, right? Thermal distortion.
So that's another argument. For example, we are using machining in process.
Okay, but suppose if I want, that means for 2 meter by 2 meter machines, you need to have a machining head?
No, you don't need to.
Suppose in the absence of machining head.
It depends on your accuracy, what you want. What's the tolerance you're looking for?
No, tolerance, because in the distortion, the XY plane, it stops your process. Now that build failure may occur.
No. What's the tolerance you're looking for? You're asking a question without putting a number in there. So what is the tolerance you're looking for? What, if it's, let's say,
let us say that
10 micrometer, then you need to machine that or whatever. If you talk about 1 millimeter, you don't need to do anything. So what's the tolerance you're looking for with your question? What are you looking for?
It's not a tolerance. Suppose I'm building a vertical wall of, let us say, 2 mm thickness on a particular section. 2 mm thickness.
2 mm.
During the building part, it may distort, right?
Yes.
How you are able to manage the distortion? Because my feature size may be 2 mm, I will be able to build. But while building, I may have a distortion. How you are able to control the distortion when you are making a bigger part?
You may just asking a very difficult question, okay? Because nobody will print a 2 millimeter sheet metal.
No.
So there is a combination of thick section versus thin section.
Correct.
So I cannot answer that question unless I see your part. Okay. It's very simple. If you give me the part, I can maybe give you some ideas. But you're asking a question I cannot answer.
So one more question. Actually, this when the build plate, actually from Z direction you are adjustable, but in XY direction is it adjustable?
Say again. That I don't understand.
That table, whatever you are moving, no, in
we are not moving anything.
Build platform.
The build platform is not moving.
Powder bed, no, the powder that whatever Z force that tank.
No,
force the tank.
The tank is
the tank is moving, no.
Yeah.
So in XY direction it is fixed, no.
Yes.
Only Z direction it is moving.
Yes.
So if a bigger part is there, that XY direction will be always fixed, like 2 meter by 2 meter, it is always fixed.
It's always fixed. So there's one frame, one structure, and it goes just up and down. That's it. And then the XY position, each laser is mounted onto this. It has its own XY positioning system.
Okay. Okay.
Can I reduce tank sizing if I want bigger? I have taken.
You can do anything you want. Yeah. You can. Yes. But you have to buy a new tank. It's the same machine. Yes. Look, you're asking questions on stuff people will say is impossible. Okay? I give you another point. Sir, no, listen to me. Listen to me. Just listen to me right now, okay? Actually, you don't need a tank. You don't need anything. But we developed something we did not right now propose because people already are shocked when we show them what we do, okay? They say, oh, this is so different, blah, 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 without thinking, right? You can print the tank. You can literally print the tank. You don't need a tank. You can just go outside. You have laser heads. You have powder. Just print the tank. You can make any shape you want. If you want to do that, you can do that. Actually, as a matter of fact, a lot of people do that because if they have complex components inside, they print outside a tube around this to stabilize this thing and to have a different thermal management. This is like a chimney for heating purpose, right? But then you don't need, we can print a tank on the outside of this. You don't need any tank per se. You print the tank yourself. So then you can make it any size you want actually. But we are not offering that right now because that's too advanced. So right now, if you say, I have a 2-meter machine, you can put a 1-meter tank in there, no problem, but you need a tank. It's not adjustable that you can take the 2-meter tank and make it a 1-meter tank. That you cannot do.
One question. There's some supportless printing technology that is coming into the market. Are you working something similar?
There's what?
Supportless printing technology.
That's not existing. There's still support in there, but it's much less.
Yeah.
That they call it supportless, but it's not supportless. So what it is the algorithm, how you support your structures. You can use less supports, but there's still some there. But yes, we're doing something similar, yeah.
For closed impellers, have you worked something similar for closed impellers?
For what?
Closed impellers.
Closed impellers, yes. But not for aerospace, for energy sector.
Okay. Just a follow-up question. What is the maximum threshold angle or the minimum threshold?
I don't know that right now.
Oh, great. Thank you.
The machining what you mentioned, that you are building some 5 to 8 layers or so, and then the spindle will come and then you will do the machining. So you will be machining only the top surface, or you will also machine the build side edges?
Actually, what I told you is not correct. What I told you is the simplified version. If you take a solid carbide, I just imagined that. That was our first step. Take solid carbide, and you spin it into a powder. And then you move the solid carbide in the powder. What do you think that is? That's actually a friction welding machine. So really what you do is you take the solid carbide, you spin it at high RPM in the powder thing, and you machine it along, so that's not going to work. So then what we developed is we have a small brush. So before you machine, the feature you want to machine, we remove the powder first, just a little bit. Then we go in with, mostly we machine the contour, meaning the outside wall of that, not much the top surfaces only once in a while, but mostly we are concerned about the contour, what we call contour. That's what we really machine there on the outside. So it's a multi-step process actually.
And when you do that, there will be some burrs or powders or things will be mixed with the powder. So
that the trick is that you set up your machining process, that the particle size are similar to what you want to print.
Okay. So that it doesn't disturb the bed.
Yeah.
Okay.
Exactly. We are even talking about grinding tools right now. So the process we have right now, or the project we have right now with they developed it looks like a solid carbide end mill, but actually it's diamond coated. It's a grinding setup. So you're grinding the surface actually with very good surface roughnesses. Okay. Any more questions? It depends. Honestly, I cannot tell you. I can give you that later.
No, otherwise 40 microns. Okay, maybe 30 microns particle size or 50 microns.
This is like a machine surface. If you machine enough away, so it's a bit tricky to answer that question. So you have to have enough top surface so that you can machine it away. If you're not, then you get whatever you get machining surface. The grinding is even better. The new grinding process we proposed to use gives you like grinding surfaces.
Any hardware you brought which is made by your machine? Any component?
Yes.
You have, we can see
here?
something?
No.
Not.
No. Actually, I'm on vacation.
You can show me components?
I'm on vacation, actually.
What is that? Vacation?
I'm on vacation. I'm not really working right now. Huh?
Any
No, that's different.
Any photograph is there? Photograph.
There are parts there. Vichin just reminded me where the backside is machined, you can see. The backside. The front side is as printed, the backside is machined.
That is a model.
Big systems, not many, maybe less than 10. From smaller wise, more. They go full range, all the options, yes. Sorry?
The bigger system, whatever you sold. The bigger system, whatever you sold, those are based, power source is laser or?
Laser, yeah.
Laser only, yeah?
Then right now we're talking laser, yeah.
Okay, laser systems only.
E-beam more. E-beam systems, not only AM, like E-beam in general, more systems sold.
Okay.
Yeah.
But based on laser, how many systems you sold?
Yeah, but the laser we are pushing right now for because of cost.
Okay.
Right? Because cost is like, I would say there's a factor 5 between the machines. If you do laser or E-beam, so E-beam is at least 3 to 5 times more expensive than laser.
Okay. Okay.
Sorry? Both. We do both.
Okay.
Yeah. Realistically, in the beginning, we will probably make some.
Second one is, I think maybe second one is you are already doing that, right?
Yes.
Services.
Service, yes.
Services, you
Yeah,
are already doing
yeah.
it. You mentioned sometime back producing some hardware for NASA.
Not NASA, but something in that direction, yes.
Any product can you show us?
No.
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 Okay.
Most of AM is ND non-disclosure agreements.
We want to get a feel. What is the kind of volume? What are the biggest size, largest size printed? That is the idea. Nothing else.
They are so we typically get into the action when we print larger than the existing machines. The current existing machine is 600 by 600 by 1.1 meter, 1.5 meter. So typically the cross section is bigger, like over 1 meter or almost up to 2 meters. But not 2 meters, actually they are less than 2 meters, 1.7.
That's okay. Probably around 1 meter by 1 meter to a height of 1.5 meter. This volume, have you delivered anywhere this kind of machine? With the laser also?
Yeah, laser.
Is it delivered anywhere?
E-beam, no.
Not E-beam, laser.
Yeah.
Is it delivered? Where is it with your factory or somewhere else, a customer's place?
Yeah, but this is all very sensitive.
Okay. But it is delivered?
Yes.
Nice.
So all this is actually called dual use technology. So most of that is okay. Thank you.
Nice presentation.
Thank
And
you.
good insight into the new technologies. Thank you.
Yeah. At least we try to do something new.
Very new. Many things. But Z-Tank is good. Z-Tank is good.
Good. So you want to do the...
We are here to represent VS Technologies. We have our facility at Cherlapalli, Hyderabad, India. And we are also setting up a new facility in Nathargal near Adibatla. So we just wanted to show you how our, what missions we have at our facility. So we are leading manufacturers of product and design. We
Change the color.
okay. We are established in the year of 2016 with expertise of 10 years in design, manufacturing and qualification of parts and products. We are committed for our reliable services in terms of quality, cost and delivery to satisfy customer needs and requirements. We are driven quality management systems, standard and procedure with ISO certification too. These are the missions which we are having in our facility in Sharlapalli, wherein one of our major strength is CNC vertical missions, 2 numbers with make of BFW, BMV 45 TC20, traverses x-axis stroke 600 mm, y-axis stroke 450 mm, z-axis stroke 500 mm. And the second mission, CNC lathe mission with the make of ACE Micromatic, maximum turning dia 270 mm, maximum turning length 400 mm, swing over bed 500 mm. Distance between centers are 425 mm, and we have 8 numbers in our facility. Now we also collaborated with Can Microtech, wherein they have the latest technology product, electron beam welding, electron beam melting and additive manufacturing. It's nothing but 3D printing machine. These are the products output which we have done at our facility, is just for your reference. Thank you, sir.
3D printing, what machine you have?
Sorry, sir?
3D printing.
No, that we have collaborated with the...
You don't have?
No, we don't have it. So we extend our sincere gratitude to each one of you and joining us today. Please join us for lunch. Thank you so much.
Stop करना. Stop చేసేయాలా?